I/O graphing can be done on live traffic as you're capturing it or on existing trace files. So I'll start capturing some traffic here. I'm going to capture traffic off the local network, and I'm not using any sort of a capture filter. Now I'll select Statistics and I/O Graph, and now it's graphing out the traffic that I'm able to see in the background. By default, it will graph all of the traffic based on either the bytes or the packet count. By default, it's set to look at packets per tick, every tick being 1 second. We can change that and say we want to see bytes per tick. There we go. Now we see the y-axis has changed. Now we're able to see bytes per tick. So here we see 500,000 bytes per tick, 1 million bytes per tick. If I wanted to, I could add a second line here to graph some other type of traffic, and I would use display filter syntax to do that. Section 8 in this course covers display filters thoroughly. So at this point I've typed in ARP. I'll click graph number 2. And now it will go through, and I should have a graph that compares all the traffic to the ARP traffic. And you can see, compared to all the traffic, ARP traffic is minimal. Now I have a file transfer going on in the background, and I just stopped my file transfer. And in a moment you should see, there we go, now we see the traffic sort of dropping off there. If I wanted to, I could get rid of graph number 1 and just see ARP traffic. And that gives me the ARP bytes per second that are happening on the wire right now. This network has a lot of ARP traffic on it. I'll bring it back, graph number 1. There we go. Now in addition, you can change the format of the graphing. So right now it's graphing as a line. I'm going to change that to an impulse, or you have the option of changing it to an F-bar, which is solid. I'll take it back to line, which is the default. Now at this time I'm going to close down this I/O graph, and I'm going to stop capturing in the background. I'm going to get rid of that trace information. I don't care about that. And I'm going to open a trace file, and this trace file is called IO-FTP upload. And this trace file shows somebody trying to do an FTP upload to a server, but the performance is really, really bad. This time what we're going to do is we'll look at the general I/O graph, and from there we'll move on to the advanced I/O graph. Now when I was in the general I/O graph, you saw me change from packets per tick over to bytes per tick, which I prefer. And this is a long trace file. It's about 815 seconds long. So as I go back in time, look at that. We've got some points in the transfer where we've got some really bad I/O problems here. Look at that. All of a sudden we drop down to almost no traffic being exchanged. And this is an FTP upload. This should all be automatic, and we should always see that there's, a nice rate of traffic crossing the cabling system. It's kind of interesting that it looks like we have a ceiling right here. It could be because our pipe is being throttled, or we've got some sort of a bandwidth maximum set for ourselves. But we shouldn't see this drop down like that in an automated process like an FTP upload. That just really looks bad. So we know that there's some sort of a problem around 600 seconds into the trace file. We can also see, let's see, where's another problem? Around 320 seconds into the trace file, we almost drop off to no traffic, and then at 150 seconds into the trace file, 40 seconds into the trace file. So there are a lot of times in here where we're having real problems. Now with a long trace like that, I might want to see more than just between 415 seconds and 510 seconds. In that case, we can change the pixels per tick, and we can say that we want to go only 2 pixels per tick. Now that lets us see a little bit more there. We can also change the tick interval. So we can say we want to plot this for a 10-second interval. And there we can see that it kind of scrunches it together. So if it scrunches it together too much, go to the pixels per tick and widen that out so it's nice and clean. Now we can see the whole entire trace file, and sure enough we can see around 600 seconds into the trace there's a problem, 300 seconds into the trace, about 150 seconds into a trace, about 40 seconds into the trace we have those problems where the I/O drops off. Now as far as the y-axis goes, it's going to figure out what the best setting should be based on the values that it's trying to plot. If you want to, you can override that. For example, right now, as it's summarizing those, it's up to 500,000 for the bytes per tick value. Maybe I want to change that. I know this is going to scroll off of the screen, but I'll change it to maybe 1 million. So there you can see we can play with the y-axis and change the way that that graph looks. I'll go back to the auto setting for that scale. And now in the y-axis area in unit, I'm going to click the drop-down arrow and I'll select advanced. Now I know this isn't going to fit on the screen completely because of the resolution that I'm doing the recording at. So I'm going to have to move this over a little bit to the left-hand side. There we go. Now we still have the graph buttons, and that's the way we turn on or off, enable or disable different graphing lines. But now, and we still have the filter capability there, so I can still say that I want to filter on ARP traffic or traffic to and from a different IP address or something like that. But now we have these calculations right here. And the calculation options are sum, count, max, min, average, and load. Load is one that you would typically use with relative time fields only. That's the only thing they can be used for. Whereas sum, count, max, min, and average are a little more useful. You can use them for different things. Sum will add up the values in a field. So, for example, maybe you want to plot the TCP lengths. We want to find out how much data is contained after the TCP header. So I'll type in tcp.len. That is the field name. That's what we're allowed to filter on, the value name. And I'll show you in a moment where you can get the whole value list of what can go into this particular field. Now I'll click on graph 1. And there, it's gone ahead and it's graphed the TCP length information. So it's gone into every single one of the packets and looked at how much payload is in there, and then it's added it up over a 10-second time and plotted it on my graph here. I'm going to change the interval back to 1 second. Here we go. So here we can see that it's just adding up the TCP lengths, and there we can see where we have some of those problems in the trace. And I'll go back in time. Look, that is just awful there. Look at that huge time there where it's trying to add up how many bytes are going across the cabling system. It just doesn't add up to anything. Now, the count on the left-hand side is something that we might use to count analysis events. For example, WireShark can track things such as the TCP retransmissions or the TCP window full conditions, or how many times there's a lost segment, or how many times there's a duplicate ACK. Let me show you an example of setting this up. I'm going to type in TCP analysis retransmission, and I'm going to do a count on that. Here we go. We can see that we have a number of points where the retransmission rate hits almost up to 10 retransmissions. And remember, I'm plotting per second. So that's an awful lot of retransmissions that occur. And here we can see there's a whole bunch of retransmissions that occur just before 500 seconds in the trace. Now here's another one that we can plot. Let's do TCP analysis duplicate ACK. And I'm going to plot that in red. There we go. Now the interesting thing here is as you learn TCP/IP communications, you'll realize that most of the time the duplicate ACKs will lead to the retransmissions. That's the cause of the duplicate ACKs. You're telling somebody else that you didn't get a packet, and you're telling them which sequence number is missing, and you want them to retransmit it to you. So typically you will see that the retransmissions will jump right after those duplicate ACKs. Now let's go back in time and look at some of these. If you find you spend a lot of time going back and forth with that slider bar, it might be time to consider your tick interval and bumping that up. So I'll go up to 10, and it's going to plot that whole thing again. And now that's really nice. So I can see where I have the retransmissions and where I have my duplicate ACKs in that trace file. I can see there's some real problems just before 500 seconds in the trace file. It looks around 480 seconds in the trace file. Suddenly I have a real jump, a real spike in the number of retransmissions. Now I'd like to show you something else that you can filter on. I'm back in the trace right now, and if you look at WireShark and you open up in this middle window, if you expand one of those areas there, such as the frame area, you'll see that there's a line that says time delta from the previous packet. Well, we can right mouse click on that and say that we want to prepare a filter. And again, filtering, the display filtering is covered in Chapter 8, but I just want to show you this. I'll say prepare a filter based on the selected, and look at that information, that frame.time_delta. Well, that's one of the values that we can place in an advanced I/O graph, and we can graph out the time from the end of one packet to the end of the next packet. So let's go ahead and do that, and this time we'll do this in a brand new window. So even though I have that I/O statistic window in the background, I'm going to select Statistics, I/O Graphs, and it's going to come up with that default basic graph. Under the Y-axis area, I'm going to select Advanced. I'll have to move it back over again. And now I want to put this value frame.time_delta. So over here I'm going to type in frame.time_delta. And I want to, this time, instead of, this isn't something I can count, there aren't just a certain number of delta times between packets. Instead, I'm going to use maximum, so that it shows me the maximum time between packets, actually the end of one packet to the end of the next packet, and it should chart that out for me. So I'll click Graph 1, and I really want to see where the slowdown is in the trace file, if there are big gaps in time. And here we go. Oh, now if I go back in time, you can see why that y-axis was all the way up to 20 seconds. Looks like right before 650 seconds into the trace, I have a jump almost up to 20 seconds. I've got another one where I have almost 10 seconds. But look, there's another one at 10 seconds. It's really, really bad performance here. So I want to look in the trace at this particular area. Now, I only used that filter up there just so I could get the syntax, so I'm going to clear that out. And I've set up WireShark right now to show me two time columns. One is my standard time column, where it's showing me time that the packets arrive compared to the first packet in the trace, so it keeps counting up. The second one is the delta time column, and I've added that by going into my Edit Preferences area and going into Columns. And you can see I've got my number column, and there's my time column, and there's my delta time column. So I'm focused on the time column because I want to get back to a little before 600 seconds into the trace. And I'll just scroll right down to that area. Here we can see I'm at 649 seconds. And I can go back in time. But now I'm really focused on that delta time column here, because just before 600 seconds in the trace, there were some big gaps in time, it looked like. So now I'm at about 569 seconds into the trace. And there we saw a 1 second jump right here. There we go, I saw a 1 second jump. But that's not enough to make those graphs pop up so high. Okay, there's a 4.7 jump at 582 seconds into this trace file. And I'll scroll forward a little bit. Somewhere in here we're going to start seeing these high numbers. Now I could sort on the delta time column and bring up all of the higher numbers to the top, and that might be faster, but I know approximately where it is in the trace. So 587 seconds into the trace, we have a 1 second delay between the end of one packet and the end of the next, then 2.5 seconds until the next packet comes along. Now we can see also around this time in the trace, we've got a number of retransmissions. Look at all those retransmissions. Look at all these duplicate acknowledgments. Wow, I should be able to see those on the first I/O graph that I built. And they should be occurring somewhere around 585 seconds into the trace. And here's that first one that I built. I'm going to go back to 1 second as far as the tick time. I want to change down to 1 second from 10 seconds. And now I want to go back down to my 500 and some odd seconds in the trace. There we go. There's this jump all of a sudden in our retransmissions and our duplicate acts, which are in red. Let's go back to the trace. I'm still looking for that really big spike in time. So I'll scroll down a little bit more. This is where I was looking before. And there, look at that. We have 4.8 seconds and 9.6 seconds delays. This is terrible. Look at these huge delays in here. And we've got retransmissions going on. So we've got packet being sent out, and we're not getting an acknowledgement for it, so we're sending it out again, not getting an acknowledgement for it, sending it out again. We keep sending it out until we finally get an acknowledgement so that we know that the other side received the packet. So in this case, we're doing an FTP upload, and we're having packet loss on the way up to the server. I really like the I/O graphing capability of WireShark. I think it really makes it clear as to what's going on the cabling system. And then when you need to explain it to someone else, you can build some of these graphs and then go ahead and do a screenshot, and you can actually show them. Usually when I show them, I try to make sure that I color code appropriately, which means that things like TCP duplicate X would show up in the color red. Something that wouldn't be so bad might show up in the color green if I'm just using a couple of different graph lines in my I/O graphing process. Because at this time WireShark doesn't have the capability to export this information out, that's when I usually do screen captures. And I use TechSmith's Snagit tool, which I really like, and I've just used that for years, so I've been really happy with it. It's worked great, and it looks really nice when you put those things into a report. And here I'm going to go ahead and just scroll backwards, and we can see, wow, 600, just after 600 seconds into the trace, just before 650 seconds into the trace, we have a huge gap in time. It went all the way up to 20 seconds. Now we should be able to toggle back over to the trace file and look about 600 and let's see, 10, 20, 30, about 640 seconds into the trace, we should have this big jump in time. Now in setting up my WireShark, I've got two different time fields here. The first time field is showing me when packets arrive compared to the first packet of the trace. And the second one is showing me the delta time, the time from the end of one packet to the end of the next packet. So I'm going to go about 600, and what did I say, 640 seconds into the trace. I'll just scroll down, and there we're around this area. Now I'm just sort of scrolling through here. One thing I could do to find these big gaps in time would be to sort on the delta time. So I've just gone back to 588, 585, etc. So I'm going to scroll through. Now here we have a gap in time. So we have 1 second from the end of this packet to this packet, another 2.5 seconds to get to that packet, which is just a huge amount of time. And we can see retransmissions. So our client is sending a packet up, waiting for the acknowledgement, didn't get the acknowledgement, retransmitted that packet up on the cabling system. So we scroll down, we've got another problem. There we go. Right before 600, we've got this gap of 4.8 seconds and then another gap of 9.6 seconds. And that's what gives us those huge gaps on the chart. But I still want to look for those big gaps around 640 seconds in the trace. Wow, they must have happened very fast there because I was just barely scrolling. Oh, look at that. Look at that. 9.5 second delay between this packet right here and this retransmission that went out on the wire, and then almost a 20-second delay until the next packet went out on the wire. So I really like setting up both the time column that'll show me the time from the beginning of the trace and the delta time columns. So let me show you what that looks like in my preferences setting. I'll select Edit, Preferences. Here we go. In the columns area under User Interface. But there's my time, and it's set up as time format as specified, which means I went up under View, Time Display Format, and set it as time since the beginning of the capture. But there is a specific format that you can use called Delta Time. So I gave it the title of Delta Time. I clicked New first, then gave it the title of Delta Time, and then in this format area there I selected the Delta Time option, and that's what created that one. Remember that if you go in and you add columns to WireShark, you're going to have to restart it. I'd like to show you now where you can get those field values that I was showing you. The field values such as TCP dot analysis dot lost underscore segment or TCP dot analysis dot retransmission. I'm on the WireShark homepage, and I'll select Documentation. And in the Documentation section, you'll see that it says Display Filter Reference, and that's where you want to go. So I'll click on Complete List of Display Filters. I'll scroll down to the index line, and here I'm interested in building some TCP display filters that I'll use in my I/O graph. So I'll click the letter T, And here you can see TCP listed there, so I'll select Transmission Control Protocol. And now as I scroll down, here are all of the values that I can use. There you can see there's my TCP analysis duplicate ACK line. And if I scroll a little bit further, there's TCP analysis lost segment, retransmissions. There's the timeout value. There's a TCP analysis window full. And remember, TCP analysis, those are the ones you do with the count calculation. So you want to count the number of times the window is full. You want to count the number of window updates. You want to count how many times there's a zero window. If I scroll further, you'll see here are the TCP fields, the individual fields in the TCP header. So the flags field. We'll scroll down a little bit more. The length field, there it is. So that's one where we can add it up, the value that's in the TCP length field. Now that's a segment length, that's not the header length. That's actually the segment length. And as I scroll down to the bottom, that's where you'll see TCP dot window size. So if you wanted to see what the window size was in a communication and have it plot it for you, you could tell it to go ahead and use sum with the window size. So add up the window size as you go through. So this is where you can find some of that information. As you saw before, another place you can go is you can go into the actual frames themselves and look at some of these time values. So I selected the time delta from the previous packet. In addition, some of the TCP packets will have some additional information in them. When we see this sequence and acknowledgement analysis, this one right here where we see the round trip time to ACK the segment was, you can right mouse click on that and say you want to prepare a filter based on the selected value. Preparing a filter isn't going to apply it. It's just going to let us see what the syntax would be. And now we know the syntax for plotting out the TCP analysis ACK round trip time. In WireShark, to get the most out of TCP time sequence graphs, you really have to have a good understanding of TCP/IP communications. Because WireShark is going to use the sequence number field values, and I'll open up a packet here, and let's go inside. There's a sequence number value, but it's a relative sequence number value. In other words, WireShark is trying to make it easier for us by doing a starting sequence number of 0. Now, we're also going to use the acknowledgement number field value to put packets in order, in the order in which they were received, the order in which they should be received, and the TCP/IP communication set, TCP, uses those sequence number and acknowledgement number fields to tell the other side which packet it expects next. And this is the way we can find packets that are out of order, packets that are missing, and this is the way we send duplicate acknowledgements to say we're missing this sequence number, we're missing this sequence number. Statistics, I'm going to select TCP stream graph. And because of the resolution that I'm recording on, you're not going to be able to see all the graph listing here. Unfortunately, the last two graphs are the time sequence graph and the time sequence graph for Stevens and the time sequence graph for TCP trace. And I'm going to look at the Stevens graph first. It's pretty recognizable because it's just a series of dots. Now I'm going to move this graph over so you can see a little more about it. But if you look in the upper left-hand corner of the graph, first of all, let's focus up there. You'll see that it's telling us that the y-axis is the sequence number value. And it also tells us what the trace is we're looking at and the direction of flow of traffic. If you were just looking at the side of communications where somebody's sending acknowledgments over to the other side, this would be a very boring graph and you wouldn't see anything because the sequence numbers are not going to start counting up. Those sequence numbers count up as data is transferred across the cabling system. So if it's just a really boring graph, close it down, you pick the wrong side of the communication. Now I'm going to bring this graph up a bit so you can see the bottom of it. And the bottom of it is our time axis. Across the x-axis it is giving us time. Now if we look at the trace and we have the trace time value set to show us the time a packet arrives compared to the first packet in the trace, we should be able to match these up directly with packets in our trace file. When we look at the time sequence graph, it should have a line going from the lower left-hand corner, gradually going all the way to the upper right-hand corner. We shouldn't see these little plateaus in a file transfer, an unattended file transfer, where you just say FTP this file up to the server and you hit enter and it just goes. It should look like this. So the end of this trace, everything looked like it went really well from about 650 seconds to the end of the trace. And there's a section here where things look like it went all right, but we have a little plateau in there. We don't like to see that. But we can see numerous points where things didn't go well. So here, between 40 and 50 seconds. There it looks like another problem about 125 seconds into the trace, another one about 145 seconds into the trace, another problem about 310 seconds into the trace, let's say. Then we've got another little plateau up here, another one. And all of these things are indications that we have problems. In order to zoom in and see those problems closely, you do a left mouse click. And every time you left mouse click, it'll bring you in closer to those problems that are in the trace. So I'm focusing on, let me pick this one, this area right here. And we'll see what happened here. Let's go right up here. Now here we can look in this trace and we can see that we've got these big areas here where we have gaps of time, and that's certainly not good. And also, these are the packets being transmitted, and the sequence number is steadily going up. If we ever see it drop back down again, we know that that's a retransmission on the cabling system. So as we move closer in here, this little dot would be a retransmission of this dot in the middle of that triple dot set there. Now I'll tell you, this is the Stevens graph, and I'm not too fond of the Stevens graph. Instead, I'm going to take you to the TCP trace graph, where we can get a lot more information about what's going on. So I'll close this down. So I'm going to select Statistics, TCP Stream Graph, and this time I'm going to go to the last option, which is the Time Sequence Graph, TCP Trace. Open that up. And I'll start out by showing you the upper left-hand corner again, where we have the sequence number, that's our y-axis. There's the trace file we're looking at. There's the traffic, the source and the destination address for the traffic. I'll move this up now so that we can see the time area down below, as well as the sequence number information. Now we can see there is this really ugly plateau area. And I want to click in and get a little closer to that plateau and see what's going on. A left mouse button will zoom you in. Shift left mouse click will zoom you out. So I'm going to click in until I've got a nice view. I don't want to click too many times because if I do, I might zoom in too fast. So we can see this area of the trace. There's obviously some sort of a problem. So I'm going to look at this portion of the trace right here. Yeah. Now you'll start to see that we don't just have one line, we have multiple lines in here. Now, the black line, as you'll see as I get closer in there, the black line is actually data crossing the cabling system. The gray line underneath it are acknowledgments that go along with those data packets, and the gray line above it is the window size. So I'll move into this area. This area is the one I'm going to concentrate on. Actually, I'll sort of focus in on all of this area. I'll move in just a little bit closer. All right. Now, it looks to me, from what I can tell, looks like we had a set of 3 packets, and now all packets can't go on the wire at the same time. So if I zoomed in a lot closer, I'd be able to see that the bottom packet went before the next packet, which went before the next packet. Each one of these little things that looks like an I is a packet. Those little black capital I's, those are a packet. The bottom of the packet is the sequence number, and then the height of the packet tells you how much data was exchanged in the packet. So I'll scroll in just a little bit closer. There we go. So it looks like we have a retransmission here. We had a set of 3 packets that went out on the wire just so close together it almost looks like the same time. And then the second packet in that set did not arrive at the destination. So over here on the right-hand side, we see the retransmission. Now these little notches that you see down below, each one of those are duplicate acts. So we look at this communication over here. There's the packet being sent, and we can count those notches. 1, 2, 3, 4, 5, 6, 7 notches. Those are each duplicate acknowledgments trying to get this packet back down. So obviously the sender had spewed all of those duplicate ACKs on the wire before it received this packet in the center, and that's what stopped it from sending any further duplicate ACKs. So it was filling up the pipe with these duplicate ACKs. Now, if everything goes well, we should be able to match up this graph exactly with our trace file. We should be able to go into our trace file about 585 seconds into the trace, see a series of packets in a row. We should see a number of duplicate ACKs, and right in the middle of the duplicate ACKs, it looks like right before ACK number 3 maybe, we have a retransmission. So let's toggle over and take a look at that. So I'm back in the trace, and now what I've done in my trace is I've got 2 time columns in there. I have the first time column, which is based on the time display format of seconds since the beginning of the capture. And then in the preferences area, I've set up a second time column, which is just the delta time column, which is showing me from the end of one packet to the end of the next packet in the trace. And I'm about at 585 seconds into the trace file right here. Now, because of the resolution that I'm working at, I need as much real estate on this screen as I can possibly get. So I'm going to move in a couple of those columns. And in fact, that time column right there, I don't need to see that level of granularity. So I'm going to go up to View, Time Display Format, and instead of putting it as Automatic File Format Precision, I'll say that I'm going to go down to the tenths of a second, and that's it. So I'm at 585.0 seconds into the trace, and I'll move that over a little bit, and I'll move the destination over just a little bit, protocol over a little bit. And now I get a little bit more information here on the right-hand side. Well, there, 585.2 seconds into the trace, we see a retransmission. But let's see what that retransmission is for. I'm going to open up the middle window, and here we can see it is sequence number 15648.181. Now I'm going to scroll up and see where the original packet went out on the wire, that 15648.181. Let me bring that window down a little bit so we can see just a little bit more. And there it is. There's the original packet right here that went out on the cabling system at 484.9 seconds into the trace. Now obviously that packet didn't get there, because if we look, a little time goes by, and we should see an acknowledgement asking for that packet. So I'm going to scroll down, and it looks like it might be this packet. I'm going to scroll to the right just a little bit. Yep. Here is an ACK packet saying that I'm asking you for 15648.181. Now we know that packet went across the wire because here it is right up here. But the other side is saying, look, I'm asking you for this packet. So here's the original ACK with a request for 181 to be sent again. If we scroll down a little further, there is a packet labeled as duplicate ACK number 1. And duplicate ACK number 1 has an acknowledgement field value of 181. This is the second request for that. It's the first duplicate of the request made above. So this is the second ACK that has that value. Here's a packet that's the third ACK that has that value. And now we have a retransmission that goes on the cabling system. And that retransmission is the 181 that was missing. Then we have a third, another time, sorry, that's actually our fourth our fourth duplicate ACK. There's our fifth, sixth, and seventh duplicate ACK. Now as we scroll through, we can see there are additional retransmissions all over in this trace file. But the time sequence graph and that trace file should match up perfectly. So anytime you work with those, make sure you toggle back to the trace file to see what's going on in the background, so that you can check and see exactly what's happening. But these are great charts and great graphs to print out to show exactly what's happening when TCP communications don't go well. Now this was an upload communication. Now I'm going to show you what happens when you look at a download of a communication, and I'll show you what it looks like when you pick the wrong side of a communication. Now I'm going to open up a trace file, and this one is called Download Bad. Here we go. Now I'm just highlighting the very first packet of the trace file, and I'm going to select Statistics, stream graph, and I'll do the TCP trace stream graph. Now when you see a graph that looks this boring, then you've picked the wrong side of the communications. There's no data being sent that way. These are all just ACK packets being sent along the cable. So close that down and pick the other side of the communication. So here I'm just going to go to the next packet. That first one was the source of 10.0.52.164, our client. And our client's the one that should be receiving the data. So we want to go to the server side, the side that's sending the data. Select Statistics, TCP Stream Graph, and again, Time Sequence Graph, TCP Trace. Now in the upper left-hand corner, we see the name of the trace that we've opened up, and we see the traffic, the source, and the destination. I'll move this up so we can see the time, a little bit more of the time information down below. There we go. And we can see that there are some problems here. Now, number one, we've got this big gap in time right here. But up here, we also have another gap in time. So I'm going to click on that, and we'll zoom in. And look at what an ugly time this is. About 60 seconds into the trace, everything looks really ugly. And look how many duplicate ACKs had to be sent at this time period to try to get this one retransmission packet. That is a ton of duplicate ACKs that were sent on the cabling system. Again, it's about 60.6 seconds into the cabling system. Now the difference here is that these packets are completely lost. Notice how we see that there's packets coming down to the client, and then there's one packet that never made it. So now we're looking from the other side. This isn't our FTP upload where we're sending everything and it's getting lost downstream from us. But this is, we're getting data from the server and packets are being lost upstream from us on the way from the server coming down to us. So that's actual packet loss right there. Here's another packet where it was completely lost. And this is our client going through and doing duplicate ACKs. And look how many ACKs it had to send out to get the missing packets. Usually the greater number of ACKs that go out on the cabling system, the greater chances that we have high latency on that cable. So let's go take a look at our trace file around 60.5 seconds into the trace. So here's my trace file, download bad, and I'm just going to line up the columns just a little bit better here. Now I'm going to scroll down about 60 seconds into the trace file, where we should start to see some problems. Now there we go. We've got some problems already. A little bit earlier I think I was seeing some. Let's scroll. Oops. There we go. We've got these retransmissions. There we go. 60.6 seconds into the trace. And look at all of our duplicate ACKs. Now right here we are asking for sequence number 1731890 from the server. And we know that that wasn't even seen because we saw that in the graph, that was just a big gap there. And we ask for it a second time, third, fourth, fifth. Those were all those notches that you saw. Look how many duplicate ACKs we get on a cabling system. Wow, that's amazing. And then we have a retransmission here a little bit later. So remember that your trace file should always match perfectly with your TCP time sequence graphs. WireShark's flow graphing is really great. It'll give you a look at the flow of the traffic, and you can see, for example, if you boot up, exactly how many systems you talk to during the boot sequence, or when you browse to a website, how many different sites do you actually go to when you think you're going to just that one site. I'm going to open up a trace file, and the first one I'm going to open up is simply the IO FTP upload trace file. And this is where there were problems uploading a file to an FTP server. I'll select Statistics, Flow Graph. Now in this flow graph selection, you have a choice. You can say that you want to see all packets or just the displayed packets if you've applied a filter. In the flow type area, you can say that you want to see all of the flow or you really want to focus just on the TCP traffic. Now in the name area there, I'm not using name resolution, so all of my addresses are going to be showing up as just IP addresses, and that's it. I'll click on OK. Here's the graph that it built for me. Now, I'm going to bring this to the upper left-hand corner, try to give us as much room as we can on this. There we go. You can see that we have just one set of, one pair communicating with each other. If we had more, we could possibly scroll to the right, or we could possibly click and drag this window open. But we can already see that there are problems in here very quickly. We see the handshake process happening up there at the top, sin, synac, ac. There you can see it on the right-hand side. And then a little bit further, all of a sudden we have a duplicate ac showing up, and another duplicate ac, and then retransmission, another retransmission, retransmission, retransmission. So it's an easy way to see when you have problems in a trace file. But let's open up a trace file where we think we're going to one website, but we're actually going to a number of them. I'll close this window out, close that window out, and this time I'm going to open up a trace file where I'm web browsing to the Microsoft website. So I'll select Statistics and Flow Graph. I'll move this up to the upper left-hand corner. Now, even though I thought my trace was just a trace of me just going out to the Microsoft website, we can see at the beginning we have a DNS query that went out. So obviously there was a little query to Google going on first. So here we have a query for Google. And we can see by the time there, it looked like I popped over to Google first, and then at some point, about 10 seconds later, I went ahead to disconnect from Google, and then I went to go find the Microsoft web page. So all of this at the beginning has to do with connecting to Google. Then we see a query. Now it says query standard on the right hand side. We can see www.microsoft.com. We got the response back, and there's our sin, synac, ac process. We can see on the right hand side sin, synac, ac. But if you look up across the top, there's our client system 192.168.1.101. This is the DNS server 192.168.0.254. We can see that's the target of a DNS query. And then we can see that this is Google's IP address at that time, where we made the handshake to Google. And we got all of our files directly from the Google page. It's not the same when we go to the Microsoft site, though. I'll scroll down, and you notice that we have, right, we know that this one right here is Google. And we see this handshake, or sorry, we see the DNS query going out from Microsoft.com. We get an answer back. It tells us that the IP address is the 207.46.197.102. So we make a handshake to that site, and we say that we want to get to the main page. Now I'll scroll down. And as we look through the trace, all of a sudden, oh, hang on a second there. There is another DNS query that my client system sent out, this time for c.microsoft.com. So we learned of another website that we had to go to when we're connecting to Microsoft.com. We're still talking to the main website until we get a DNS response back from that query, and it gives us the IP address of 207.46.130.149, and that's who we will talk to next. So there's the SYN packet going out to another IP address. Now we've got two communications going on simultaneously. We're talking to www.microsoft.com, and we're talking to c.microsoft.com. And the nice thing about the flow graph is that it shows very clearly when you have multiple connections simultaneously running on the cabling system. Now I'm going to close this down, and I'll show you another trace. Now this one is a DHCP communication. And DHCP looks a little weird sometimes. So we'll open up the statistics flow graph area, say OK. And here's DHCP. Now in this case I have my client system that does the DHCP discover. My client system doesn't have an IP address yet, so the packet comes from 0.0.0.0, goes out to the broadcast address. There it is, our DHCP discover. Now here we can see an echo goes out, a ping packet goes out, a ping request goes out on the cabling system. There's no ping response. Turns out that that's my DHCP server, and it's testing to see if anybody is using 10.1.0.2. Nobody answers back, so it turns around and it offers me that address. It now sends it to the new address that it is offering to me. So it looks really weird. This column right here is the same device as that column right there. So here we can see that the offer goes out explicitly to 10.1.0.2. but my workstation doesn't take it yet. My workstation sends its request back to the DHCP server through the broadcast address using that 0.0.0 address again. And then we can see that there is the final piece of the DHCP process where the server sends back our final acknowledgement. From this point on, our client can actually start using 10.1.0.2 to use everything, to do everything. So DHCP just looks a little weird when you look at it in a flow graph. Now I'd like to bring up another graph, another trace file. And this one is a system that's infected. And it's got some malware on it. Now I'll select Statistics and Flow Graph. Now I want to show you the difference between general flow and TCP flow. The first thing I'll do is I'll open this up with general flow. Now this is the boot sequence of an infected system. Now we've got a scroll bar down here so you can tell when our system boots, our infected system boots, we talk to a number of devices. And across the top it will build the whole entire list of devices that it sees our system talking to or anybody talking to in that trace file. It'll actually put together all the different flows in the trace file in this one area. So there's our system, and our host system in this case, the one that's having the problems, is the 24.6.125.19. So we've got a DHCP request going out. Remember, it looks weird when you see DHCP, but that's our system going out and doing a DHCP discover packet. The filter that was set up for this trace was on traffic to and from the hardware address of this device. And the DHCP ACK didn't go to that hardware address, it went to the broadcast MAC address. So the ACK didn't show up, the last piece of the DHCP transaction there, which is weird. But our system's just coming up, and we've already got somebody sending us handshake packets, trying to make a connection to our system. Our system isn't answering back yet because it hasn't even initialized its IP stack. One of the strange things you'll see in flow graph here is that ARPs are dropped. So our ARP packets have been dropped. So I'm going to move this. In the actual trace file, you'll see that packet number 2 is an ARP packet. And packet number 4 is an ARP packet. And packet number 6 is an ARP packet. But when we look at our flow graphs, we don't see those ARP packets on the cabling system. So you'll see as I'm scrolling, looking at that top column, I don't see the ARP packets. Now, if we look a little further down in here, we can see we've got all these handshakes going on. We've got a request to connect to the update Keep Alive McAfee server. I'll see we can see a standard query going out, DNS queries going out. And I'll scroll down. There are handshakes going on. This is all talking to the McAfee server. We're doing an update of our virus detection tool. So this is what just the basic looks like now. I want to close this window out. This time, instead of general flow, I'm going to choose TCP flow. Say OK. Now it's a simplified view of what we were just looking at. We don't have all the detail about the file that we were doing a lookup on, or anything like that. Here we can see the communications, and we can see there are a number of handshakes coming into our host that are from other systems just trying to connect to our host. So there's a SYN packet, SYNAC, ACK. Lots of folks trying to connect to our host. Lots of handshake packets in here. So that's a great trace file to look at when you're playing around with the TCP flow graph area. The numbers that you see there in the gray are the port numbers that each side of the communication is using. So if I scroll over here, I can see these are port 80 communications. It's all of our McAfee stuff. And I'll look a little further here. There's port 80 communications. Scroll that window over. And scroll down even further. See if we have anything else interesting in there. There's our port 80 communications. There's communications. Port 4899 coming in. That's a SYN coming from somebody else, and our system does not support that. So we see just a reset going back, SYN reset. That's what it looks like when you have a TCP scan going on in the flow graph. But you can see you lost all of that detail that you had before. I'm going to close this down. I'm going to open up another trace. Now this one, I'll bring up evil program one more time, because in evil program, if we look at the flow graph, as long as we do general flow, we get a lot of information about what's going on. You can scroll down through this trace, and there you can see there's a messenger query, messenger packet coming across the cabling system. There's this DCE RPC traffic going on the cabling system. We don't really want to see that kind of stuff. Now, of course, I'm running this at a very low resolution for the recording process. On your system, you could maximize this on your window and be able to see all sorts of stuff. There we see another DNS query going out for updates.virtumon.com. And that's part of the problem in this trace file. There's the GET request to get a malicious code off of a server. So it's a really nice trace. If I wanted to, I could build a filter up here. See, I'm only interested in the IRC traffic. Apply that filter. Oh, no IRC traffic in this trace. Let me open up a trace that does have IRC traffic. I'm going to pick up a trace called client dying. Now, because I had that filter up in there, it's going to automatically apply it to this trace. Clear it out, you'll see there's lots of other traffic. Put it back in, and we can pull out just the IRC traffic. Now, if I go to the flow graph area, I can say that I want to look at just the displayed packets. Say OK. And now all I'm doing is looking at the flow graph of the IRC communications. WireShark can report on the service response time, or the time between a request and a corresponding response, for a number of different protocols. I'm going to open up a trace file here, which is a really interesting one. It's a client that has multiple protocol stacks running on it. It's got TCP/IP and it has IPX, believe it or not, sweet little IPX. It's also connecting to a legacy Novell NetWare server over IPX, and it's connecting to an NT server. So this is an interesting one. This is a legacy client of mine. I'll scroll down, and we can just scroll through. You can see that we've got IP communications. We've also got some IPX addresses in there. Now, under statistics, I'm going to select service response time, and here you can see the list of protocols that are supported and applications that are supported with service response time. Now, I know that Novell uses NCP, Network Core Protocol, so I'm going to select that. At this point, if I have a lot of different traffic in there, I can go ahead and filter out. I could filter based on just one IP address or just one IPX address, etc. But I'm going to go ahead and just create the stat. And it processes all the packets. And when it's done, I'll have a nice table to look at. So let me open this up. And here we go. It's grouped according to what type of a communication it is. So there are some file system calls, there's some connection calls, directory services, file server environment, extended attributes, some bindery stuff, messaging, packet burst, time sync, and general synchronization. Then I can also look based on the function information. So we've got end of jobs, get the current size of a file, read from a file, and we can see the number of calls for each of those. So there are 508 end of job notices, 333 get current size of file, 298 read from a file, etc. Now, in addition, if I click on any one of these along the path, I can see that I have subfunctions for NCP function code 21. There's subfunction code 2, which is disable broadcasts. There are 8 disable broadcast calls. Now, I also have the minimum service response time, the maximum service response time, and the average service response time. So obviously, if you're looking at a communication that deals with something like, such as these NCP statistics, and you see a really high average service response time, there's an upper layer problem there going on. It's the time that it's taking for the request to go across the wire and the reply to come back. And we would compare that to the wire latency time to make sure that it's not big delays across the cabling system that are causing this high response time. I'll click on function code number 22, and there we can see scan directory information. Now this is just a boot sequence, and there are 115 different queries for directory information, which seems like an awful lot just to boot. Here we can see get file server information. 186 times that client made a query to get file server information during the boot process. That's excessive, and that's just not normal. If these other tabs don't have anything underneath it, it just means that there are no subfunction calls underneath those function codes. Now here we have an ugly one. Obtain file or subdirectory information. It's NCP function code 87, subfunction code 6. And this user system made 1,592 queries for file or subdirectory information during just a boot sequence. To search for a file or a subdirectory set 803 times, initialize the search 550 times. There are way too many calls being made during this client's boot sequence. Something has gone terribly wrong. And I'm just clicking across here to see if there's anything else interesting. Fragmented requests, and the time sync. Get the time, and I think that's about it, other than the NDS calls. So now that I know that I've got way too many of these obtain file or subdirectory information calls on the wire, I can close this window down, cancel this window out, and scroll through and see what these queries are for. As I scroll through, there we've got a read property value of net address. All of a sudden we'll see another read property value for net address, another one. This is all the NT connection process going on. And there we go. There's another read property value for the network address. And create a connection service. And we're looking at object information. Read the attributes, changing a connection state, destroying it, resolve. And the interesting thing with this client is, look, read property value for net address, read property value for net address. The client seems to be in some sort of a loop. Look at that, read property value for net address. Over and over and over again, the client makes the same query. So this is obviously part of the problem and why Teresa's boot sequence is taking so long. I'll show you how long it takes. I'm going to go to statistics and summary. And here we can see between the first and the last packet, 367 seconds. That's a bad boot sequence. But our service response time can show us that it's some sort of an upper layer problem because we're seeing way too many queries of the same type. Here we go again. There are file system calls, 4,606 file system calls on the cabling system. Way too much. So we know it's not a cable issue here. This is some sort of an upper layer problem. WireShark has a very simple way of providing you some statistics having to do with DHCP or bootp. First, I'm going to open up a trace file. Now, this is a normal DHCP boot sequence. I'll select Statistics and bootp DHCP. If I had a lot of different DHCP communications in there, I could filter based on one value in that DHCP set. I could filter based on one MAC address, but I'm not going to do that. I'll just go ahead and create the stat. I'll give it a moment and it'll come up. And this is a normal DHCP boot process when you're not within your leased time. You do a discover, get back an offer, then a request, you get back an acknowledgement, and you're done. I'll close this out, cancel out that window. Now I'm going to open another trace file. And this is called DHCP good third boot whiner. This is a DHCP workstation that's booting up and it's not within its lease time, so it's going to start with this discover. Now if everything goes well, we should see just the number 1 in each of those DHCP packet types, but we don't. We see discover. There are 3 discover packets, 3 offer packets. We now have an inform packet, 2 act packets, and 1 request packet. So now we quickly know that something's going wrong and we're going to have to do some DHCP analysis. There's our discover. There's the offer packet that came back. This client doesn't like that. It says, no, 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 no. This is what I'd really like. Let me do another discovery. Service says, you know what? Forget it. This is what I'm offering you. I don't want it. Let me do another discovery. Server says, I'm sorry, this is what you're being offered. And then finally the client says, okay, I'll go ahead and take that. So that's what it looks like when a client comes up and says, no, I'd really like to have the last address. And I'd really like to have the last address. Let me open up another DHCP communication. This DHCP client goes through the process of renewal, but unfortunately the DHCP server is no longer there. Now we know there's a problem because we're only capturing that client's traffic. And when we go to create the stat for DHCP, we have too many packets there. Look at all those request packets. We should see discover, offer, request, act, just one of each if the client's outside of their lease time. Or if they're in their lease time, again, we should see one request and we should see one acknowledgement, and that's it. So I'll close this down, cancel it out, and now we can see the client making the request of the DHCP server to extend the lease time. No answer. 6 seconds later, the client makes another query. No answer. 305 seconds later, there's my delta time column. 305 seconds later, the client gives up and says, forget that. Is anyone out there? Now the client's starting to sweat bullets. Can anyone help me? Can anyone help me? Makes another request to the broadcast address. No. Another request to the broadcast address. No. Etc. And it keeps going that way until finally the DHCP server comes up again, gives the client the offer. The client's still doing discovery. That unfortunately, the client had to drop its IP address. It's already making a request using 0.0.0.0, so it couldn't wait any longer. It had to give up, and fortunately the DHCP server was back up, gave it an offer. Client keeps coming back with additional requests, or discovers, excuse me, and then finally we finish it all up at the end with a request and an acknowledgement. For more information on how DHCP works, you can take a look at the WireShark University TCP/IP analysis course. WireShark can give you numerous HTTP statistics, but if you first look at them, you might think that they're a little boring, but they're really not. I'm going to start by showing you sort of a normal plain HTTP browsing session, and then I'm going to show you what it looks like when you go to a site where they've got ads being served to you by third-party sites. You think you're going to one site, but you're really not. So the first trace I'm going to open up is a trace file called http-packet-level. Now this is somebody going to our packetlevel.com website. I'll open up statistics and HTTP, and there are 3 statistics that we can track here: load distribution, packet counter, and requests. I'm going to start by just showing you the load distribution information. Now, as in many of the statistics, I can add a filter here. So if I was looking at numerous HTTP transactions, lots of people talking to different servers, I could filter out one conversation if I wanted to. But this trace file was created looking at only one conversation to start with, so I don't need to apply a filter. I'll click Create Stat, and sometimes you need to wait a little bit for it to populate the information in here. Now, first thing I'll do is I'll look at the HTTP requests by server address. So here, now 128.241.194.25 is the IP address of www.packetlevel.com. And we see that that server, that IP address is associated with that server. In addition, it's kind of strange here, but there's our client, and our client is associated with that address, although that's not our client's address here. But that's the server that our client is talking to. We can see the requests based on the host information, and we can see these are the 2 hosts that are associated with packetlevel.com communications. I've got my client system, and I've got the server. Okay, that's not terribly interesting there. So I'm going to go ahead and cancel this out, and I'm going to go back to statistics and select HTTP, and now we'll look at the packet counter information. I don't need to apply a filter. There we go. So there's one HTTP request that was sent out, and there it is. It's a GET request. And these are the response packets that came back. Now this is interesting because it will tell you when there are redirections or any type of server error, or if there's just informational replies coming back. Success, we can see that it's an HTTP code 200, which means OK. So that's nice. We didn't see any sort of errors in that process. I'll go ahead and close this window out. Now I'm going up to Statistics, HTTP, and Requests. And this is the one that I really like. I'll create the stat. These are the requests by HTTP host, going to packetlevel.com. And these are all of the files that the client requested in order to load that page. Really nice. Now, besides getting the request information, you see the packet count that it took to get that file, as well as the rate that it was going at and the percent of the traffic that matches that request. Now let's look at an ugly web browsing session. I close that out. Now I'm going to open up a trace file going to ESPN. This is called http-ESPN. And I usually do use the ESPN website as an example of a really muddy, yucky, disgusting HTTP communication. So I'll select Statistics, go to HTTP, go to Load Distribution first. I don't need to build a filter. I'll just create the stat. So here we have HTTP requests by server address. Look at all of these addresses. Now there's my client, but look at these other IP addresses associated with this communication. This is really interesting to look at in a flow graph as well. So here we can see there's ESPN. Oh, there's espn.go.com. There's static.espn.go.com. Now there's some ad site that they're sending me to. Another ad location that they're sending me to. Starwave. And I can scroll out. Look at all those different locations that my client has to connect to when I say that I want to go to espn.com. And that's horrible to see. Ad.doubleclick.net. Ugh, yuck. All right, so this is pretty interesting when you look at this information. I'll scroll back up, and I'm going to go ahead and collapse that first one and bring this second part back down, because now I have the host address listed. So in one fell swoop, I can see all of the different hosts that I connected to just when I said http://www.espn.com. I'm going to close this window out, and I'm going to cancel this window out. Now I'm going to go down under Packet Counter. I'll create the statistic. There are the HTTP request packets that my client made. It made 2 GET request packets, and here's the classification of the responses. Now here we can see we've got some success packets. 272 packets are success packets, and there are redirections sending us to different websites. Hey, this is moved. This was found, and let me tell you where to go to get it. There are also some things listed as client error, which is interesting. A 404 error is classified as a client error, which means you blew it, you went to the wrong page. Never classified as a server error or a web designer error or anything. It's always classified as a client error. So this is kind of interesting to see that we have some redirections in there, and we have a 404. We have 2 404 file not found errors that came up in the background. I'll close this window down, cancel this one out, open up Statistics, and go to the last area in Statistics, which is the request area. Create the statistic. Now here are the requests made by the host. We can see these are the sites that we went to, and this is what we requested. This is what we were told to go get at each of those sites. There's our ad stuff. We can see that we've got ad data that's being requested. There we're just getting some information. I mean, when you go to the espn.com website, you're going to see it's a really, really busy website. And even though it doesn't seem like it takes a long time to load, it actually does. But there are things happening on your screen, to make you all happy and feel like there's something going on and you're never just left in limbo. So this is actually pretty interesting. The HTTP statistics are really interesting. If you get a chance, go ahead and browse to some websites and run through the statistics HTTP area to see what comes back, especially in the load distribution and packet counter areas. WireShark's round-trip time graph is built based on a comparison between when a segment goes out with a certain sequence number, the acknowledgement that comes back as an acknowledgement for that particular sequence number. So it's a matching up of the sequence number and the acknowledgement number field values in the TCP header. I'm going to open up a trace file that has a problem with downloads. In this trace file, we have a user that's going out to a website and they're trying to download the OpenOffice suite, and it just seems like it takes forever. So we can graph the round trip time and see what's going on in the trace. Now, just like in our time sequence graph, we've got to highlight the direction of the communication that data is flowing. So there's our client 10.0.52.164 making a connection to the server on port 80, the HTTP port. Now the client is going to be downloading the OpenOffice application, so that's not the direction that data is going to be flowing. I'm going to highlight packet number 2, and that's the packet I'm going to create the round-trip time graph on. That's the direction of the traffic. I'll select Statistics, TCP Stream Graph, Round-Trip Time Graph. Now again, I'm recording with a much lower resolution than I would normally use, and this window is not sizable. So I'll have to move the window around in just a moment after I show you the upper left-hand corner. Here we see the name of the trace file, and we see the source of the traffic, and we see the destination of the traffic. Remember, if you come up to this window and you just don't have anything plotted on it, then you're not looking at the right direction of the traffic. You're looking just at the side where the acknowledgments are being sent. And you really want to look at the side of the traffic where the data is being sent. Make sure that the source is the one that's sending the data. The round-trip time value is used in the y-axis here, and it's automatically defined based on the counters that WireShark sees in the packets. And this is a terrible, terrible download because we can see that the round-trip time at some points hits 1 second in round-trip time and even 0.7 seconds. This is really pathetically slow. I'll move this graph up now, because you'll see that the x-axis is the sequence number field value. So that can help us pinpoint certain problems in here. We can look at a certain area where there are problems, and we can find the sequence number, and then we can go into the trace and look for that specific sequence number. I'll show you a little trick on how you can do that. So this area right here in the trace seems to be a problem area. I'm just going to highlight or click on this area down here because I want to see approximately where that is. And I'm basing that on the sequence number values. There we go. I'm just moving in. So it looks like we're somewhere around sequence number 1750000. So 1,750,000 is the area I want to look at as far as TCP sequence numbers when we start to see these problems. I'll close this window down, and I'm back looking at the trace file here. Now, the sequence number field, I'm just going to cheat here to find a packet that starts with a sequence number up at 1,750,000. I'm going to right mouse click on the sequence number field, go to prepare a filter based on the selected. Now it comes up as tcp.seq for sequence is equal to 0. Well, that's not what I'm interested in. I'm looking for TCP sequence number values that are greater than 1,750,000. And that'll take me right to that spot in the trace. So I'll apply that. Remember that display filters are covered in more detail in section number 8 of this course. So here I am. I'm up at this area now, but you've got to remember that I've just used that as a cheating way to go to the right packet. After you apply that filter, you want to get rid of it because you're only looking at one side of the conversation, because the other side of the conversation has a different sequence number altogether, and it's not counting up like this side is. So I'm going to clear out that filter now that I'm at packet 2404. Okay, great. That kind of tells me where to look. And I can see I'm right in the middle of a problem already. So I've got duplicate sequence or duplicate acknowledgments out on the cabling system already. Now in the TCP header, let me move this up a little bit. In the TCP header, you'll see this sequence and acknowledgement number analysis section, where when you highlight a packet, it will tell you what, if it has the ACK bit set in the flags area there, it will tell you what packet it is the acknowledgement for. So it tells me that packet number 2408 is the acknowledgement to the segment that's in packet 2407. So here's packet number 2407. So here's my server sending back an acknowledgement to my client. And I can see the time is 0.005. As I scroll down through here, you see it looks like we've got a pretty standard ACK time that's showing up of 0.005. So we've got packet loss here, but we don't have any really high numbers. Now we're starting to get up to 0.01. One of the ways that you can spot problems easily in the trace when you're working with a lot of packets and you don't want to sit there and scroll through all these different packets in there is to sort on the delta time column field. So I'm somewhere around packet number 2500, and I'll click on the delta time column twice. I'll go to the top here, and these are the delta times that are in this trace file. And we can see we've got some really big problems here around packet number 375. Eek, that looks terrible. No wonder this is such a bad download. I'll scroll through, and here we've got some pretty high times right here, packet number 2861. I'll sort again, and then use the Find button, the Go To button, to go around 2800 into the trace. Now here we can see I've got a packet, and it tells me this is a really fast acknowledgement. Look how fast that is. That's because it's my client acknowledging back to the server. And I'm sitting on the segment with the client. The client's pretty quick. But there's the server's time. Pathetic. Really slow. Scroll through. Oh, 0.15. That's not very good at all. Each time I see these high numbers, I'm pretty sure it's the server that's sending these high round-trip time values. Ooh, there's a 0.147. There's a 0.17. There's a 0.2. And it seems like it's just getting worse when we look at the trace file and we scroll through it. So you've seen that there are cheating ways that you can go through and you can see where the problems are in trace files. And you can search or look for packets according to a certain value in that sequence number field. Now let me show you what it looks like when you look at a download that's good. I'll open up a trace file called download good. And you don't even have to go through the packets to see that this is a lot better. I'm going to highlight the traffic in the direction that data is going to be flowing. So the source will be from this server to our client. I'll select statistics, TCP stream graph, round trip time. Now, just by looking in the upper left-hand corner, we can already tell that this is a lot better file transfer than the last one. Because look at our y-axis. The y-axis does not go up to 1 second anymore. It goes up to 0.2 seconds now. That's the maximum. So we already know that we don't have all of these packets, all of these round-trip times way up in these higher values. Come down here, look at the sequence number value. There we go. We can see that there appears to have been a problem right around here in the trace, though. Some sort of a strange thing. And every once in a while we have this sprinkling of a slowdown. But that slowdown there is nothing compared to that last trace. So a lot of times when you look at round-trip times, just bring up the graph and look at what that y-axis is. And that will tell you the maximum round-trip times that are in the trace. Then find the area where the little dots are going a little bit higher or clumped up higher. Locate that sequence number and then go into the trace and find the traffic around that sequence number to see what happened.